first talk will be Tathagata, who won the Honorable Mention for Best Dissertation Award on this topic, Foundations of Human-Aware Planning, a Tale of Three Models.
Thank you. Hello everyone. I am Tathagata from Arizona State University. First of all, thank you for this honor and giving me the opportunity to talk about my thesis again here. The topic of my thesis is Foundations of Human-Aware Planning, a Tale of Three Models. So let's begin with what we mean by human-aware planning. So, as we know, the topic of sequential decision making is about finding out what to do next. What is the correct sequence of decisions to make? However, most of the systems in the real world are not standalone systems. They work with humans in the loop, and so we have to be able to model their beliefs, intentions, and expectations of the systems that we are building. However, most of the work in planning traditionally has been in dealing with standalone systems. We do not model the humans explicitly, and that can lead to all sorts of problems in terms of cleaning and in terms of explaining behaviors as well. So, for example, here's human-aware planning all gone wrong. Like 2 hours before I defended my thesis, Google came up with this news recommendation about a news article about how a student failed their defense. So it's not just about modeling the human, it's about doing it correctly. And that's the goal of this thesis. How can we model the human in a way that will help our planning systems in order to interact with the human in the loop? So what are these three models? Well, to begin with, we have the traditional view of the planning problem. There's an agent with a model, and given the model, we can find a plan. However, when you are working with the human, what you're dealing with is joint plans. So the plans have some parts that are coming from the human and some parts that are coming from the robot. And so there's a task model of the human involved in this process. So that's the second model. This model allows you to anticipate what you can get from the human and how you can deal with the human explicitly. So how you can deal with them, how you can avoid them, how you can assist them, etc. There's also the third model, which is the expectation that the human has on the robot. So this allows you to conform to the expectations of the human, or if you cannot conform to those expectations, it allows you to explain your behavior in terms of the differences in those expectations. So these are the three models that form the core of the human-aware planning task. The robot's own model, the human's task model, and the human's mental model of the robot. So in the first part of the talk, I will briefly go over how you can use the human task model to produce novel behaviors with the human. So the running example that I will use in the talk is that of a search and rescue domain. So there's a human and a robot involved in a search and rescue task. And what specifically we are going to look at is how you can use the human model to coordinate with the human without having to communicate that much. So in general, you can use the human task model to do teaming in the general sense. In my thesis, I looked at the specific problem of minimizing communication. So interaction without prior coordination, or ITC as we call it in this room. So two very specific ways of looking at this is what I call planning with resource conflicts. So these are things, these are ways to plan when there are conflicts with the human's intentions, and how you can avoid those conflicts by planning out the human intentions. And then there's the idea of actually affecting the human's plan, and so that's planning for serendipity, when you are actually improving the human's plan by changing parts of the world in order to make their plan better. So for example, if you're dealing with conflicts, one thing as the robot that you can do is to figure out what the possible human plans are and try to compromise on your own optimality to preserve the human's intentions. So that's the compromise part of it. But you can also use artifacts of the human's plan to improve your own original plan. And that's the opportunism part of it, because the human's involvement in the same process actually helps part of your planning problem. Similarly, for planning for serendipity, we looked at this idea of how to how to help the human when the human doesn't expect it. So here the human is going to do a triad in the location at the top left, and they are going to pass by the corridor regardless of what the robot does. So the robot is anticipating that behavior and trying to put a medkit on the way so that the human does not have to go and fetch it. So this kind of behavior again improves the human's plan, and the robot is able to do it without any communication. So I won't go into the details of these algorithms, but the key takeaways here is that you can use abstract representations of the expected plans of the human to come up with these the reasoning techniques of how to assist or avoid or deal with the human. And one of the things that I looked at in this part of the work is how to use integer program-based planners to model those complex constraints with the human. So that's about the human task model. The real part of it that I would want to focus on in this talk is the human mental model. So that's the expectation that the human has on the robot. So one of the problems that comes with having expectations is when those expectations are wrong. So that means that if the robot is doing the best possible plan it can, because the human's expectations are different, even if the robot is doing the best it can, the human would find better alternatives. So those we call inexplicable plans, because the plans of the robot are being evaluated by the mental model, not the actual model. So as a robot, you have two options here. You can make explicable plans, which means that you sacrifice optimality in your own model, but try to be explicable to the human or conform to their expectations. Or you can make explanations, so you can be optimal in your own plan and provide explanations when the expectations diverge. So let's look at a brief demo of what this looks like. So back in the search industry domain, the robot here is searching a map, and the external here is the human who is not present in the scene but has access to the map. And what often happens in those scenarios is because it's a disaster scene, part of the map would have evolved from the actual blueprint of the building. So the external commander or the human would have started with one version of the map, and it would have changed during the process of the operation. So then there would be rubble that have closed off parts of the path. There might have been walls that have collapsed, so new paths may have opened up. So the plans that the robot will be making would be diverging from the expectations of the human. And so the question is, how does the robot reconcile with this diverging model? So in this example, the first plan that you're looking at, this one, is where the robot is actually clearing off obstructions in order to make a plan that is closer to what the human would expect. What that means is that the robot here is doing a suboptimal plan just to make sure that the plan looks closer to optimal in the human's mental model. In the explanation scene, the robot would ignore that plan and would be optimal to itself. So it's taking a different route. And in the top left, it was giving explanations of what changes have happened in the model so that this plan now makes sense. So that's the usual scene with planning with the mental model. So if you're trying to be explicable though, you can't use the mental model directly. That's because the human's expectation might be so far off that it's too costly for you or it's infeasible. So for example, if the human expects you to fly and you cannot fly this, then there's no way you can be explicable. So the usual way of generating explicable plans is to not use that model directly, but use that as a guidance or heuristic in the search to get towards more and more explicable plans. So what happens if explicable plans do not exist? The other side of the coin of dealing with model differences is this idea of explanations. And this explanation, one of the key parts of my thesis is looking at how you can take the human's expectation into account while giving those explanations. So an explanation cannot be a solution. You cannot be talking to yourself with respect to your own model, because the reason that explanation was required in the first place is that the human had a different expectation of the model. So we came up with this notion of model reconciliation as a way to formalize the explanation process. And the way we look at this is, so the starting point is that the robot has produced a plan, and the explanation is in the form of a model update to the human, so that at the end of the process, both of them agree that that's the best plan possible. So the plan is both optimal in the robot's model and in the updated human model. And this sort of an explanation actually has some basis in the literature, in social sciences and in human-human interactions that look at the social, contrastive, and selective properties of explanations. I won't go into the details of that. Particularly about the contrastive property, what we are doing here is we are making sure that the human cannot come up with better alternatives once the explanation process is over. So the contrastive property is that we are contrasting against all possible plans. One of the key findings of this sort of setup is that there are many ways you can find this model update. So we looked at different forms of these explanations. Some of them have conflicting properties. So for example, you might be trying to minimize the amount of information in the explanation. You might be trying to minimize the amount of time to generate the explanation. And we looked at these different kind of explanations, different properties of these explanations in our HK paper. But one thing I would like to point out is the explanation MC and MME, which are very curious ways of finding explanations. MC here is the minimal amount of information that needs to be given to the human so that they can make sense of the plan. While MMEs are the minimal amount of information that needs to be given to the human, and after which the explanation never becomes invalid. And it turns out that computationally, depending on the amount of model difference between the human and the robot, MMEs and MCs can be more difficult or easier to find. But the way we go about finding these explanations is what we call model space search. And the idea of model space search is to search in the space of models that are enabled by the differences in the two models, the robot's model and the human's mental model, and find the model in where the optimality condition holds, so where we can contrast the given plan with the space of possible plans. So going back to our discussion on the differences in models and what to do with it, for a human-aware planner then, the real question is how can we balance these ideas? So we can explain, we can be explicable. From the traditional planning point of view, we are not making a plan given a model. We are finding out which is the model that we should plan in, given the mental model and the robot's model. And so we actually looked at variations of this model space search, where we saw how we can balance this off optimally and find even shorter explanations than minimally complete explanations. And that's the same algorithm that was going on in the video demo that we saw, where we were changing the parameters of the algorithm to figure out whether the robot should explain or the robot should be explicable. Of course, the human-aware planning is not complete without actually evaluating that with humans. So we actually did a slew of studies to figure out how humans responded to these different behaviors. In particular, we abstracted out different parts of the search and rescue domain and presented that to the user to see how they responded to these kind of explanations. We did this experiment in two parts. One, where we actually asked the humans to be the explainers and try to match that with the different kind of explanations that we came up with. Two of the key findings, one was that in certain circumstances in limited communication, they actually matched the NC and FDs that we looked at before. Also, they did come up with other explanations that we did not look at in our work, which also kind of informs what other kinds of explanations that we can use in this process. We also flipped the table and said, evaluate the explanation that we did come up with, and are they happy with those explanations? And in most cases, they were actually able to find out the key properties of the explanations of the plans that the explanations were trying to preserve. So that's indicative of the fact that the theoretical properties of the explanations we're trying to preserve is also preserved when they are interacting with the human. So that's about the task model and the mental model. The human-error planning is not complete unless you look at the entire process of not only behavior but communication as well, because not everything can be signaled through behavior. So even if you have even if you have reconciled models, there might still be different behaviors that are possible. So you need to communicate your intent, or you might need to communicate your explanations in the form of different forms of interaction modularities. So in the last part of the thesis, I look at this idea of mixed reality interactions to help human-robot teaming. The particular thing that we look at here is this is a way to get out of the ambiguity in natural language interactions and look at specific ways in which we can communicate intentions to the human in the loop using natural language vocabulary. So the key idea here is, can we use a much more constrained vocabulary to disambiguate interactions at the time of execution? Can we use that to generate plans that are easier to communicate? And can we use that to reconcile models as well? And this leads to this idea of projection-aware planning, where you're not only communicating intentions at the time of execution, but at the planning time, you are changing your plans based on how easy it is to communicate. So the setup kind of looks like this. You could talk to the robot through the mixed reality cues, and the robot talks back to you in the form of those cues. This forms a much more constrained vocabulary, and you can talk in those terms and how it changes the plan of the robot and how it changes your perception of what the robot is doing. In terms of planning, the specific thing that we looked at is the idea of action and state value projections to project out parts of the domain. I won't go into the details, but the general idea is to have a domain-independent vocabulary by which we can have these interactions. And of course, mixed reality can be applied outside of human-robot teams in communicating with the cars, in decision support systems, in embodied systems like smart rooms, etc. And so the same topics will find applications again and again in different settings like this. So in conclusion, I looked at these 3 different models that you can work with in order to build human-aware systems. I looked at many different applications of it in the thesis. I covered some of it in here in terms of applications to the human-robot scene, but there's also a separate line of work on how to apply the same concepts in terms of decision support. These are the red ones of the papers that I covered briefly in this talk. And the work has gotten a lot of impact and support from the community. And finally, a thank you to my lab mates, my ASU, IBM, and especially my advisor Rao for making this work possible. So I will end here, and we're happy to take questions.
Questions for the speaker? What is the most annoying human thing that planning systems have to deal with?
I would say suboptimality, because humans are not great planners. And so one of the biggest future works that comes out of this is to how to deal with the fact that they won't be making the right plans or even sound plans per se. And dealing with that complexity is hard.
I think the battery on the other wireless is dead. Next question.
Do you see any need to go deeper? I don't mean like deeper. I mean like nested model, or is this sufficient? Have you found science?
There's actually some literature on how deep you need to go to model interactions, and usually the idea is one level deep is enough for most applications. But yeah, you could go deeper, but we couldn't find much use of that. At some point, it's like a trade-off between the complexity of finding things as well.
Okay, one last question while we're waiting for the next person to get set up.
Did you consider any antagonistic models?
The most of my work was in collaborative sync. There is also work from a lab that looks at the other side of the coin. So you can think of the other side. So if you're being explicable, you can also use the same techniques to obfuscate your actions. So make it more harder for the human to detect what you're doing. And the talk after this talk, I will talk about some of that work.
All right, let's thank the speaker.